What you cradle in your palm represents one of humanity's most extraordinary achievements, not merely a device, but a condensed universe of human knowledge, engineering prowess, and global collaboration. This is the iPhone 17 Pro Max, but its origin story stretches back through time and across continents, a narrative far more epic than its sleek titanium frame suggests. We're about to embark on a voyage that begins deep within the Earth's crust, traverses the most advanced manufacturing facilities ever conceived, navigates a global logistics network of mind-boggling complexity, and culminates in this intimate moment of unboxing. This is not merely a story of assembly, but of transformation where raw, unrefined elements undergo a metamorphosis so complete they emerge as a pocket-sized portal to human knowledge. Prepare to witness the alchemy that turns sand into intelligence, or into beauty, and ambition into reality. Our journey begins millions of years in the past, with geological processes that concentrated the very elements we need. The backbone of this device is silicon, the second most abundant element in the Earth's crust. But not just any silicon. The quest begins in the quartz mines of North Carolina or the Spruce Pine region, locations chosen for their exceptionally high purity quartz deposits. Here, miners extract massive veins of milky white quartz, a form of silicon dioxide so pure it's already 99.9% SiO. This raw quartz undergoes an initial crushing and washing process before being transported to metallurgical-grade silicon facilities, often located near massive hydroelectric dams in the Pacific Northwest, where immense electrical power is readily available. Inside these vast, humming industrial halls, the quartz is mixed with carbon sources like wood chips, coal, and coke, and fed into a submerged arc electric furnace. Electrodes plunge into this mixture, creating temperatures in excess of 200 Celsius. In this inferno, a violent chemical reaction occurs. The carbon greedily bonds with the oxygen in the quartz, releasing carbon dioxide gas and leaving behind molten 98-99 pure metallurgical grade silicon that is tapped from the bottom of the furnace. But this rough, bluish-gray material is still light years away from the computational heart of a chip. It must undergo a second, even more precise purification, the Siemens process. The metallurgical silicon is ground into a fine powder and reacted with hydrochloric acid in a fluidized bed reactor at 300 C, transforming it into a cocktail of silicon chlorides, primarily trichlorosilane HSICl. This gas is then distilled in massive 80-foot-tall distillation columns, a process repeated multiple times to achieve an unparalleled level of purity. Removing boron and phosphorus contaminants to parts per trillion levels, this ultra-pure trichlorosilane gas is then introduced into the final deposition reactor. Inside this sealed chamber, thin rods of ultra-pure silicon, known as seed rods, are heated to over 100 C by passing an electric current through them. The superheated gas molecules contact the searing surface of the seed rods and decompose, depositing elemental silicon atom by atom, growing the rod outward over several days. The result is a magnificent, shimmering polycrystalline silicon ingot, or bulls, with a metallic sheen, typically 2 meters tall and 300 millimeters in diameter. And of such purity it is considered one of the purest substances on Earth. The bull, while pure, has a chaotic internal structure. For the single crystal perfection required by microchips, it must undergo the Czochralski process. The polysilicon bull is broken up and loaded into a quartz crucible within a growth chamber filled with an inert argon atmosphere. The furnace heats the silicon to a precise 1:1 C, just above its melting point, creating a shimmering silver vat of molten silicon. A seed crystal, perfectly aligned to the desired atomic orientation, is then dipped into the melt. It is then withdrawn slowly, at a rate of millimeters per hour, while both the seed and the crucible rotate in opposite directions. Through a phenomenon known as necking, any dislocations in the crystal structure are eliminated, and as the molten silicon freezes onto the seed, it copies its perfect single crystal structure. The result is a new, flawless single crystal ingot, a monolithic grain of silicon that will form the substrate for billions of transistors. This perfect crystal is now ready for its transformation into wafers. Using a revolutionary diamond wire saw, where a single wire hundreds of kilometers long is looped thousands of times around precisely aligned grooved rollers, the ingot is sliced into wafers thinner than a credit card. The wire, moving at speeds over 60 kilometers per hour, is embedded with diamond particles that abrasively cut through the silicon with microscopic precision. The wafers are then lapped with a slurry of alumina particles to remove sore marks, and chemically mechanically polished with a colloidal silica slurry to achieve a surface so flawless that any atomic level irregularities are measured in angstroms. This mirror finish surface is the pristine canvas upon which the A19 Pro chip will be masterfully painted. The process of photolithography is the heart of chip fabrication. The wafer is first coated with a light-sensitive polymer called photoresist. It is then placed in a stepper scanner, a machine costing hundreds of millions of dollars. Inside, a beam of extreme ultraviolet EUV light with a wavelength of just 13.5 nanometers is generated by firing a high-power laser at microscopic droplets of molten tin. This EUV light, reflected through a complex series of ultra-precise mirrors in a vacuum, projects the circuit pattern for the A19 Pro chip onto the photoresist, hardening it in the exposed areas. Subsequent chemical baths etch away the unhardened resist and the underlying silicon, creating the nanoscopic trenches and towers of the transistors. This process is repeated over 50 times, building the chip layer by layer with atomic level precision, creating a 3D structure of breathtaking complexity. Home to over 20 billion transistors, while the brain is being etched onto silicon, the body is being forged from metal. The iPhone 17 Pro Max's frame begins as grade 5 titanium Ti6Ai4V, an alloy of 90% titanium, 6% aluminum, and 4% vanadium, prized for its exceptional strength-to-weight ratio and corrosion resistance. This alloy originates as a sponge from the Cleanroom process, where titanium tetrachloride itself derived from rutile ore is reduced with molten magnesium in a sealed, argon-filled vessel. This sponge is then mixed with the alloying elements, pressed into electrodes and melted in a vacuum arc remelting VAR furnace. An electric arc is struck under a vacuum, melting the electrode and allowing impurities to float away, resulting in a much more homogeneous and pure ingot. This ingot is often subjected to a second melting in a plasma arc furnace for aerospace-grade purity. The resulting titanium ingot is then forged under immense pressure and heat into a billet, which is then hot rolled into long bars of the required diameter. At the Foxconn or Pegatron facility, these titanium bars are cut into smaller, brick-like blocks. Each block is meticulously clamped into a 5-axis CNC milling machine. The machine, guided by CAD data accurate to within microns, begins its symphony of destruction and creation. Diamond-tipped end mills, rotating at tens of thousands of RPM, scream through the solid metal, shearing away microscopic curls of titanium in a shower of coolant. They first perform roughing, removing large volumes of material to create the basic internal cavity. This is followed by semi-finishing and finally finishing passes, where progressively finer tools carve out the precise contours, the speaker grill holes, the button recesses, and the camera bump with an accuracy that defies human perception. A single frame can take over 100 minutes to mill, generating significant waste, all of which is collected for recycling. The machined frame, now structurally complete but rough to the touch, enters a post-processing area. It is tumbled in large drums with millions of fine ceramic beads, a process called abrasive blasting, to achieve the signature, velvety matte texture. It then undergoes an anodization process. Immersed in an electrolytic bath and subjected to a specific voltage, a controlled oxide layer grows on the titanium surface. The thickness of this layer, determined by the voltage, causes light interference, creating the specific color, whether cosmic black, Sierra blue, or titanium white. This anodized layer is not a paint. It is a part of the metal itself, highly resistant to scratching and wear. The components, the logic board, the A19 Pro chip, the cameras, the displays now converge in the final assembly facility. The heart of this operation is the cleanroom, an environment where the air is constantly filtered and recirculated, maintaining a positive pressure to keep contaminants out. Technicians, clad head to toe in bunny suits, are but attendants to the main performers, the robots. The process begins with the board stuffer, a bare-printed circuit board PCB. A complex sandwich of fiberglass and copper traces is loaded onto a conveyor. Surface mount technology SMT machines, equipped with banks of reels containing thousands of tiny components, spring to life. A laser scans fiducial marks on the PCB to precisely orient it. Then, at blinding speeds, robotic nozzles pick up microscopic resistors, capacitors, and integrated circuits from the reels and place them onto pre-tin solder pads on the board with an accuracy of 25 microns. The populated board then flows into a multi-zone reflow oven, a precise thermal conveyor belt that heats the board according to a specific profile, melting the solder paste and creating permanent electrical connections without a single human hand touching the components. Meanwhile, the A19 Pro chip, having been tested and sliced from the silicon wafer, is prepared for installation. A robot applies a microscopic dot of thermal interface material to the chip's surface. Another robot, using a vacuum collet, picks up the chip and aligns it over the socket on the logic board using a high-precision vision system. It places the chip with a gentle, unwavering pressure. The board, now with its brain attached, is then carefully guided by a robotic arm and secured into the waiting titanium frame. A perfect fit born from digital design, the camera assembly is a feat of nano-optics. Each of the four lenses, made from custom-molded glass with new graphene oxide hybrid coatings, is housed in a brass barrel. Robotic arms, in an environmentally controlled enclosure, assemble the lens stacks, the image sensors, and the complex sensor shift stabilization mechanisms. Each assembled camera module is then placed into a calibration rig. Here, it images test charts under a variety of simulated lighting conditions. The data is fed back to the module, and micro-actuators inside the barrel make infinitesimal adjustments to the lens alignment, calibrating for tilt, shift, and decentering to ensure absolute optical perfection. The final, dramatic act of hardware assembly is the display lamination. The titanium frame, now containing the logic board and batteries, moves into a station. Above it, the display assembly, a complex laminate of cover glass, polarizer, OLED panel, and touch sensor, is held by a robotic jig. The environment is purged of dust. A protective liner is peeled from a layer of optically clear adhesive on the frame. Then, with flawless, even pressure, the display is lowered onto the body. The bond is instant and perfect, creating a seamless, waterproof seal. A newly assembled iPhone is merely a potentiality. It must now prove its worth. The first spark of life is administered not by a button press, but by a bed of nails test fixture. Spring-loaded pogo pins make contact with test points on the logic board, delivering power and the first bootloader code. The screen illuminates, showing the factory diagnostics screen. The device is alive, but untested. IT now enters a gauntlet of quality control that is both exhaustive and ruthless. It travels on a conveyor through a series of automated test stations. Audio test. It enters a sound-damped anechoic chamber. Speakers play a complex set of tones from 20 Hz to 20 kHz, while calibrated microphones inside the chamber listen for any distortion, rattling, or imbalance. Simultaneously, the device's own microphones are recorded as they capture a series of chirps and spoken phrases. Analyzed for fidelity and sensitivity, display and touch test a high speed. Ultra-high resolution machine vision camera scans the display as it cycles through solid colors red, green, blue, white, black. It detects any dead pixels, sub-pixel defects, or color uniformity issues invisible to the human eye. Then, a multi-fingered robotic probe taps and swipes across every millimeter of the screen thousands of times, verifying the accuracy and responsiveness of the touch sensor. Wireless and connectivity test. The device is placed inside a Faraday cage, a shielded room that blocks all external signals. Inside, it connects to simulated cell towers, Wi-Fi routers, and Bluetooth beacons, testing the speed, range, and integrity of every wireless protocol. The new satellite connectivity is tested using a simulated satellite signal. Camera calibration test. Each camera is tested again, now in its final housing. It images complex test charts under calibrated D65 daylight and a tungsten lighting. Powered software analyzes millions of data points from the captured images, checking for autofocus speed, white balance, accuracy, lens flare, geometric distortion, and the precise alignment between the four cameras for seamless zoom transitions. Environmental sealing test. The device is moved into a pressure chamber. A sensitive pressure sensor detects the minute change in air pressure as the chamber seals, confirming the device's internal volume. A small pressure is then applied. A stable reading confirms the waterproof seals are intact. Any device that fails any test, for any reason, is immediately ejected from the line and sent to a diagnostic station for root cause analysis. Only the flawless proceed. The hardware-verified iPhone is now a pristine vessel, ready for its digital consciousness. In a massive server farm adjacent to the assembly line, thousands of iPhones are simultaneously placed into shielded racks that connect to their Lightning ports or a new wireless provisioning interface. A customized build of iOS, specific to that device's model and storage capacity, is flashed onto the NAND storage at gigabit speeds, but this is more than a file copy. This is the moment the device becomes unique. Its secure enclave, a separate microprocessor, is provisioned with a unique and changeable identifier UID and a set of cryptographic keys that are burned into its hardware, never to leave the chip. This is the root of its security. The cellular and Wi-Fi modules are calibrated, with their individual RF characteristics stored in memory. The device is registered in Apple's global database, its serial number now married to its digital identity. Once provisioning is complete, the device is wiped clean, leaving it with a fresh, pristine installation of iOS, ready for its users' first hello. It is then given a final, meticulous cleaning by soft, lint-free cloths attached to robotic arms, removing any microscopic fingerprints or dust accrued during testing. The journey from product to package is a mesmerizing display of high-speed, precision packaging. The iPhone, now complete in every way, glides into the packaging line. The box itself is a feat of engineering, made from 100% recycled wood fibers sourced from managed forests, its white color achieved without chlorine bleaching. A robotic arm unfolds the box's base with a series of precise folds and tucks. Another robot places the iPhone into its molded pulp tray, a custom-fit cradle made from recycled paper. The USB-C 4 cable, with its new textured, fray-resistant braiding, is coiled by a machine into a perfect, consistent loop and placed beside it. The documentation, now reduced to a single, elegantly embossed sheet of paper and the iconic Apple logo stickers, is placed on top. The lid is lowered, and as it closes, a small magnet embedded in the paperboard clicks into place. The final step is the laser-etcher. A high-powered laser beam traces the Apple logo and iPhone 17 Pro Max text onto the lid, vaporizing a thin layer of the inkless white coating to reveal the slightly darker brownish-gray recycled paper underneath, creating a subtle, sophisticated, and debossed-looking finish. The product is now ready for its global voyage. The moment the box lid closes, its barcode is scanned and its digital passport is activated. It is placed on a pallet with hundreds of its identical siblings, wrapped in weather-resistant plastic, and loaded by autonomous guided vehicles AGVs into the waiting container of a temperature-controlled truck. This truck drives to a massive regional distribution hub, a facility so vast its roof can span hundreds of acres. Inside, it's a city of robots. The pallet is broken down, and individual iPhone boxes are placed into a chaotic storage system, a grid of thousands of bins, managed entirely by a fleet of hundreds of orange-wheeled robots. These drive robots, about the size of a large coffee table, scuttle across the grid, lifting and moving entire shelves of inventory to human pickers at the periphery. When you click buy, your order triggers a digital chain reaction. A signal is sent to this hub. A robot retrieves the shelf containing the iPhone with your specific serial number. A picker, guided by a light on the bin, grabs your iPhone, scans it, and places it on a conveyor belt. It travels through a tunnel where it is automatically scanned. Wait to confirm nothing is missing, and a shipping label is precisely printed and applied by a high-speed printer actuator. Your iPhone, now in a plain brown outer box, is sorted into a chute leading to a truck destined for your local airport. It is loaded into the cargo hold of a Boeing 777 freighter, often on a flight operated by UPS, FedEx, or Apple's own logistics partners. Within 12–18 hours, it has crossed an ocean. It arrives at a local distribution center, is sorted onto a delivery van, and begins the final, terrestrial leg of its journey, its location now trackable by you in near real time, and then, the culmination of this global, year-long endeavor, a knock on your door. A notification on your phone, a package in your hands. You are the final, crucial component. As you slice the tape, you are performing the last step in a process that harnesses the power of stars to purify silicon. The force of continents to forge metal, and the ingenuity of millions to write the software. You lift the device from its tray. You feel the cool, seamless union of polished glass and textured titanium, a feeling made possible by thousands of hours of industrial design and metallurgy. You press the side button. The screen erupts in light. The word hello appears, not as a mere greeting, but as a testament to the fact that humanity can take the raw materials of the earth and, through a symphony of collaboration and innovation, transform them into a key to the collective knowledge of our species. The journey is complete. The story now continues with you.